Hi guys, my name is Chris Wu.
I'm Kenneth Falsetto,
I'm Howard Chen.
This is our video tutorial for Physics 40B.
and today we'll be learning heat engines.
You guys learned something new today and hope it helps you guys with your finals.
Okay, so today we are looking for the problem 21.53. A heat engine using a diatomic gas follows the cycle shown in the figure. Its temperature at point 1 is 30 Celsius. So this is 30. And for part A, determine work done on system and Q and delta ETH for process 1 to 2. So if we want to know the WS, we need to, which is just the area from 1 to 2, which is the whole thing. Then will be, because this is 0.5 and 0.1 to 1.5, so will be 0.5 times 40 minus 10, which is 40 minus 10, plus 1.5 minus 0.5 times 40 minus 10 divided by 2. This is the area of this triangle, and this is the area of this. And here we can get 30. So now, because this is all under cubic centimeters, we need to convert into cubic meters, and also we need to change the ATM into Pascal. So it will be 30 times 101,325 Pascal times 10 to the negative 6. Then we get 3.04 joules. Now we need to calculate the temperature at T2, which is here. We can use P1 V1 over T1 equals to P2 V2 over T2, and we can get 0.5 times 10 over, that is 30 Celsius, will be 30 plus 273 equals to 1.5 times 40 over T2. So we can get T2 is equals to 3636 Kelvin. Okay, now we already know the temperature at T2, so we need to calculate the total amount of moles. And we know the formula is N is equals to P1 V1 over R T1, which is equals to P1 is 0.5 times 10. 10 is the volume, times 101325 times 10 to the negative 6 over R is 8.314 times 273 plus 30. So for N we get 2.011 times 10 to the negative 4 mole. Now we already know the N, so we need to calculate the delta ETH. Which is, because this is diatomic, so we need to use that equation, which is F over 2 and R delta T, which is equals to 5 over 2 times N is this, 3.011 times 10 to the negative 4 times R. R is 8.314. This is mole. This is joule. Mole. Kelvin. Times the difference between the temperature from here to here, which is 3636 minus 303 Kelvin. And here we get 13.9 joules. And also for from the first law of thermodynamics, we can get delta ETH is equals to W plus Q, and WS plus Q. So we need to get Q, right? So Q is equals to delta ETH plus work done on the system, which is equals to, we add these two together, will be 13.9 joules plus 3.04 joules is equals to 16.9 joules. So now the work done on the system will be this, and Q will be this, and delta ETH will be this one.
Now we're working on part B, and this time we're determining the process for 2 to 3. And we know that 2 to 3 is isochoric since the volume is constant. And since we know that the volume is constant, we know the first law of thermodynamics, our work would end up being 0. And now what we need to do is solve for Q. And then Q equals F to the 2N R delta T. And since we know it's diatomic, it's 5/2 N R T. And our delta T from earlier was 3636 Kelvin. Now we need to look for T3. And to find T3, we can use this equation. T2 equals P3 T3. And we got that since we know it's constant volume. And our P2 is 1.5 ATM. And our T2 is 3636 Kelvin from earlier. And P3 is 0.5 ATM. T3 is what we're solving for. For T3 we get 1212 Kelvin. And then since now we know that T3 is 1212 Kelvin, let's solve the delta T, which is just T final minus T initial. So in this case it would be T3 minus T2, which would end up getting delta T equals negative 2424 Kelvin. Now we can plug it all in here, and we get Q equals 5/2 2.011 times 10 to the negative 4, 8.314 joules per moles Kelvin. And then our delta T is negative 2424 Kelvin. And then we end up getting our Q, which is just negative 10.13 joules. And since we know that our Q is equal to delta ETH, our delta ETH should also be negative 10.13 joules. Now we're gonna work on part C, which is going from 3 to 1. And what we know from going 3 to 1 is it's isobaric since the pressure is constant. And what we can derive from that is our work equals P times delta V. And we know that our P is just 0.5 ATM times times our delta V, which is our V final, would be 10 minus 40 centimeters cubed. And then we need to change that. We need to change both of these into Pascal. And this one into times 10 to the negative meters cubed. And we get
Or
Negative 1.52 joules.
negative 1.52 joules. Now we gotta solve for a Q. Or no. Did I solve for Q or ETH next?
I think I got ETH.
Alright. Now we can solve for ETH, which is just, and our delta T, and what we remember is our moles is just 2.011 times 10 to the negative 4 moles, 8.314 joules per Kelvin. And our delta T should be T1 minus T3, which is 1,303 minus 1,212. And our delta ETH will end up being
Negative 3.8.
negative 3.80 joules. Now we can solve for our Q with this equation again. Delta ETH equals negative WS plus Q. And we can move that to that side. H plus WS equals Q. And we got negative 3.8 joules plus negative 1.52 joules. So our Q will end up being, let's see, negative
5.32.
5.32 joules.
Okay, so part D asks, what is the thermal efficiency of the heat engine? Well, the thermal efficiency is basically just how much, it's an assessment of how much heat given into the engine is actually translated to the work put out by the engine. So we can put in an equation where our efficiency, just eta, is equal to the total work put out over QH, which is the energy given in. We know that the total work is actually just the sum of the three processes there, the 3 points. So work out is equal to work 1 over 2, 1.1 to 0.2, plus the work from 0.2 to 0.3, and then the work from 0.3 to 0.1, completing the cycle. And then we also know that QH is 16.9 joules. So the total amount of work given here is actually just 3.04 joules from 0.1 to 0.2, and then 0 joules from 0.2 to 0.3, because we know that 0.2 to 0.3 is isochoric, and then the work done on 0.3 to 0.1 is negative 1.52 joules, all over 16.9 joules, and that gives us 1.52 joules over 16.9 joules, which leaves us with 0.09, and then we multiply 0.09 by 100, and that gives us 9%. So that means 9% of the total energy given into this engine is actually translated into mechanical work, whereas the rest, all 91%, is just wasted as heat energy. So that's part B. That's our final answer, 9%. So part E asks, what is the power output of the engine if it runs at 100 RPM? So the definition of power is just that is the amount of energy or work over time. And then we know that the amount of work is actually 1.52 joules. And meanwhile, we also know that the engine is currently running at 100 RPM. And RPM just stands for revolutions per minute, which is just the amount of cycles per minute. So we know that the engine runs at 100 RPM, 100 cycles per minute. And then we can translate that to seconds, as seconds are SI unit. As we know that in each minute, there are 60 seconds. So this gets canceled out, and then we're left with 100 over 60, 5 over 3, roughly 1.67 cycles per second. So with this info, we can get the total power by multiplying the total work done by this frequency right here. So 1.67 cycles per second. And that leaves us with 2.5 joules per second, which is equal to 2.5 watts. And that's our final answer for part E.
Hope you guys enjoyed the video.
Like, share, comment.
If you guys want to watch yesterday's video, click here. If you want to watch a previous video that we made, click here.
Thank you.